I'm really honored to be here, and thank you very much for inviting me to speak. I mean, during the morning session, I was thinking that my memories about Gorkov don't go as far back as memories of many others, and when exactly was the first time I heard the name. And I think this was some very bleak, really bleak winter day about this time of the year, beginning of January. Freezing rain, wind, dark night, somewhere the center of Moscow in a big square. I was talking to a friend, there was at that time there was a electronic news billboard, like running news line, like what we have in Times Square. Yeah, and so the running news were basically headlines from newspapers, and the year was about 1980, so the headlines were not particularly exciting. And what made the situation even more bleak, that there was some plainclothes police guy who was circling around us trying to listen to the conversation. And then suddenly, I saw something in the news running line that brightened everything up, and it was saying that today a big discovery was registered by the State Council for Inventions and Discoveries. Gorkov and Abrikosov discovered Gapel superconductivity. And I mean, there were a bit more detail about that, but somehow that, I think that was my first memory, not the last one, luckily, but the first memory of Gorkov, and it really brightened up that very dark day. So what I'm going to talk about are two topics on what I'm now working on, which is hydrodynamics and electron fluids. None related to superconductivity directly, although the second topic may be a little bit related. But I think an excuse is that Gorkov himself did some important work on hydrodynamics, and so we're allowed to speak on that here. So just, in the introduction, if you look around on the human scale, almost everything we see can be described by conservation laws for fluids and gases and solids, and that's what we call hydrodynamics. So everything on this picture, waves and boats and people and air and everything is subject to hydrodynamics, and so there is no question that human scale, it's a very important approach. When you take into account conservation laws only, quantities which are conserved when particles interact and ignore everything else. And then one can ask a more refined question: if we think about metals, can one describe transport of metals in a similar way? And usually the answer is no. Usually the picture is that electrons are moving freely like pinballs, losing their, dissipating their momentum at disorder. But there are some rare situations when electron-electron collision time is faster than time of collision with disorder. And in this case, one can think about it in a hydrodynamical sort of way. Say that electrons exchange momenta very quickly, and so each electron forgets about its momentum very soon because it collides with another electron. However, because momentum is conserved in two-body collisions, it becomes a shared collective variable, and as such acquires existence over quantity which is independent of the particles that transport it. And one can understand transport in the system in a hydrodynamic sort of way. And there are several types of systems where these ideas are applicable. And I mean, the idea itself, by the way, is not, not particularly new. It goes back to the 60s, mid-60s, about the time when I was born. So it's really old by now, starting from Gurdjieff, and then later on it was developed by many other people, including some people here, Sabir in the past millennium, and in this millennium by Steve, and many others. And there are two kinds, but I mean, now it's interesting again because there are systems where this is realized and experiments are possible. And there are two kinds of systems. There are systems where disorder is very weak, and so electrons obey Fermi liquid laws, but disorder is so weak that that we can ignore disorder mostly and think about electron-electron collisions only. And then there's another kind of systems where quasi-particles lose their meaning, like strongly interacting systems, and in those systems one can also come up with a hydrodynamic description. I will focus mostly on the first type systems because that's where experiments are now being done, and maybe mention the other one briefly. So one system of that type is graphene. In graphene, we have near the Dirac point, we have very strongly interacting particles because at low doping, at charge neutrality or small doping away from charge neutrality, interactions are very strong. And because of crystal symmetry, collapse are not allowed. So if we treat crystal momentum in the same way as we treat particle momentum for gases, we end up with viscosity and hydrodynamics for electron fluid, and we can try to describe what's going on in graphene using hydrodynamics. And this has been a theme of many works recently, and I will talk on a few things in a direction that we worked on, which is the interesting geometries where viscous effects are most prominent, and new collective phenomenon. So the geometry I will be interested in will be a constriction. When you try to push a fluid through an opening. And for free electrons, or for Fermi gas, this is a well-studied problem. It goes back to the work by Landauer, who related conduction and transmission, and based on that could predict that conduction, that there will be finite resistance associated with this opening, even if electrons are moving freely through it. And the value for resistance can be calculated from Landauer formula by counting the number of channels, or more easily can be calculated from Sharvin formula. Sharvin actually did this experiment with point attached to a surface of metal, and derived a formula saying that conductance is proportional to the cross section of the contact. Later, this was realized, in a nicer way, in split gate structures with high mobility gallium arsenide, where you can change the width of the opening gradually by applying potential on gates, and then you see not only that conductance indeed varies linearly with width, as you can see from the slope, but also you can see quantization steps, each being E square over H. I think Dima Khmelnytsky wrote one of the early papers on that. But then the question is, this ballistic conduction is often taken as the fundamental limit for how high conductance can be. And one can ask, is this really true? Now, actually, before we get there, let me just, for the sake of what we're going to talk about in a moment, let me give you Sharvin argument pictorially. One can ask, let's say, if this is an electron, what's the probability for this electron to go through the opening? And you can see from this picture that this probability can be calculated by from the angle at which this opening is seen from electron position. And so if its velocity is in this angle, it will pass, and if it's not, it will not pass. So basically, there is a relation between conductance and phase space for the angles, and if you integrate that over possible positions of electrons, you'll get Sharvin formula. And so what we're going to ask is whether this is really the highest conductance possible. And one can see very quickly that if you allow electrons to interact and scatter on each other in a momentum-conserving way, then conductance should go up. And one way to see it is to go in the extreme hydrodynamic limit when electron fluid flow can be described by Stokes equation, and then there is some flow that is pictured here in blue, and then if this is an electron, it will be doing a zigzag motion colliding with other electrons, and it will be carried, it will be sucked into that constriction and carried through regardless of where its initial velocity is pointing. So I can go back and say that if my initial velocity is such that the electron wouldn't pass and I introduce collisions, now it will pass. And so from that we can say that conductance should go up. One can do a simple estimate based on Stokes equation, say write down the relation between Laplacian of velocity, viscosity, and electric field driving the system. And then this equation can be interpreted as a current field relation, and you can write down scale-dependent resistivity in this way, where gamma, the scattering rate, will be viscosity times k squared. And now if I set k of order 1 over the width of the constriction, I'll obtain conductance. And as you can see from this formula, it will scale as the width of the constriction squared, so it faster than linearly. And comparing to ballistic value, you see that the ratio is the width divided by mean free path. So if mean free path for electron-electron collisions is shorter than the constriction width, conductance will be enhanced, right? And if it's much shorter, it will be greatly enhanced. So that's why, in this problem, somewhat counterintuitively, introducing interactions gives higher conduction. Right, so that's interesting. Yeah, question? Right. Now, more interesting is that in a system like graphene, one can go between these two regimes continuously just by varying temperature, because carrier scattering is proportional to T squared in the Fermi liquid, T squared divided by Fermi energy. So either by varying temperature or by varying doping, by varying Fermi energy, one can change the scattering rate and go continuously from ballistic conduction to viscous conduction. And the prediction is that if you increase temperature in graphene, conductance will go up, right? And so that's what we were interested in, and started working on it. And the team is two amazing students, both undergrads, and two collaborators from Israel and UK, and a lot of inspiration came from Andrea Gaim, and not only inspiration but also data obtained by two amazing students. And so the experiment they did, basically in line with this proposal, was that they made a device with many constrictions of different widths, and they run current through the system and then measure potential drop on each constriction independently, and so they can measure resistivity for each constriction as a function of temperature, as a function, and different constrictions having different widths allow to measure scaling with width. And so what they see is that at 0 temperature, conductance obeys Landauer or Charvin formula without any fitting parameters. Dashed lines are fit to Charvin expression. There is a factor of 4 instead of 2 because in addition to spin degeneracy in graphene, there is also valley degeneracy. And then if you increase temperature, you see that resistance goes down. And it goes down when the temperature increases about up to about 100 Kelvin, then starts going up again because at that temperature, electron-phonon interaction starts playing a role. Sorry for my voice, I'm running cold. And then the straight lines is Charvin prediction for ballistic carriers, no fitting parameters, and dashed lines that you barely see is theory. Then they also did control experiment. In that device, there was an area where you could measure 4-probe resistance, and in that region, everything behaved normally, so they could confirm that there's nothing funny with the sample. And at that point, I think we got convinced that this is indeed what's going on. So now the model. Model. In the model, well, there are 3 regimes. Ballistic, when mean-free path is very long, viscous when it's very short, and crossover. And in these 2 regimes, one can write down a simple analytic expression. Charvin and Stokes provide that. And crossover is the problem that one needs to deal with using Boltzmann kinetic equation. And it's a challenging problem because one needs to solve it in this geometry for mean-free path being comparable to the width of the constriction. And so there is a complicated story about this was done, how this was done, and a paper that describes it. Maybe for the sake of time, let me not get into that. One can map this problem, 2-dimensional problem, on a 1D problem and derive some integral equation. This integral equation resembles what one gets in quantum scattering theory. And then that integral equation can be handled, and then from this equation, one can confirm both limits, and then in the crossover limit, one can obtain potential distribution, solving 1D equation, and then reconstructing 2D potential, one can obtain potential distribution on the entire plane, and then taking potential drop across the constriction in response to unit current, we get resistivity, and that's how we do the calculation. And there are interesting features here. As you can see, potential has this non-monotonic dependence with horns and so forth, and people, and that's a signature of viscous regime, by the way, and people are now trying to actually detect it by scanning techniques and see it directly, but negative E at the edge. And that's in the viscous limit. In the ballistic limit, these non-monotonic E dependence go away. Now, if you take conductance calculated in this way, sorry, resistance calculated in this way, and do it for different widths, you can confirm that conductance scales is a function only of the width divided by mean free path. And so this is calculation for different values of both parameters. And if you now scale, you see that all the curves collapse on one curve. And so that's a sanity check that calculation is right. And after that, a surprise comes, because if you now calculate conductance by inverting resistance, you find a straight line. And this straight line is really straight line, as straight as it can be numerically. And so from that, and it has the right asymptotic values at infinite mean free path and very short mean free path, agreeing with what we know from Charvin and Stokes. And that from that, we can write an expression for conductance, which is a sum of the ballistic and viscous expression. And so that's the answer. And now, using that, we can go back to experiment and analyze data and see that indeed the deviation from ballistic value has this expected W square dependence on the width. And so the agreement looks really good. Right. So how much time is left?
About 5 minutes.
Good.
What is the value of viscosity?
Uh,
You know the value.
So the mean free path at these temperatures and densities varies from few microns to 0.2 microns. And then kinetic viscosity is obtained from that, multiplying by square of the Fermi velocity and dividing by 4. I mean, whatever. Are you asking about universal bound for entropy? Yeah, we are about, I think, no, it's like near neutrality point, probably a factor of 10 or 100 away. Yeah. Right. Okay, so then, I mean, let's forget about this for the next 4 minutes. Now, there is a totally different, well, not totally different, but related but different topic, which is about what actually happens microscopically if you want to understand collisions, how viscosity arises from collisions in a two-dimensional Fermi surface. You realize very quickly that something interesting happens, and that interesting thing is the following: if I take two quasi-particles near the Fermi surface, the thermally broadened Fermi surface, and ask, suppose they can collide with energy conservation, momentum conservation, and Pauli blocking taken into account. What is the rate for these collisions? Then you find that the only type of collisions that can happen are collisions in which particles collide head-on. So particles that come at some generic angle can only undergo small angle scattering, and I will explain why in a moment. So only these particles can collide. And when they collide, each of them can scatter in a head-out way at some arbitrary angle. And so because this is what's going on, in this problem, there is a very different relaxation rate for even and odd harmonics of the electron distribution function, Fourier transformed as a function of angle, right? So that's unusual. And it's not the case in 3D. In 3D, all harmonics are roughly decaying with roughly the same rate, and we can discuss why. And 2D is quite different. So why is that? If you take your mechanics 101 picture for two-body collisions, let's say particle 1, particle 2 collide, then we know that if we go to the center of mass, in the center of mass, collisions will be head-on. And then particles, after colliding head-on, will go head-out. And we can draw this kinematic circle showing where particles can go. So particle 1, particle 2 here, circle drawn on this segment as diameter, and then diametrically opposite points are possible positions of particles 1 and 2 in momentum space. Okay. Now, if you add Pauli blocking to that, superimpose this with thermally broadened Fermi surface, then you see right away that most of the phase space is forbidden by Pauli blocking because particles cannot scatter here. These states are occupied. And they also cannot scatter here because if one particle scatters here, there must be another particle scattering in a diametrically opposite point. So because of that scattering change in angle can only be of order T over Fermi energy, i.e. very small. And the only way out of it is to make particles collide head-on. In this case, this kinematic circle that we draw coincides with the Fermi surface, and then scattering by any angle is allowed, right? But then we'll have a price to pay, right? And so this looks a lot like what we have in BCS Hamiltonian when we think about coherent pair scattering on the Fermi surface. However, here it's a statistical, not coherent scattering process, but constraints are very similar, right? And so, I mean, we're not the first ones thinking about it. There's been some literature, but unfortunately or fortunately, most of it has not been done. Right, and so if you now take this a little further and say that you have collision integral, that if you linearize eigenstates, which are harmonics of cylindrical harmonics, the even parity harmonics and the odd parity harmonics will have very different relaxation rates. Then you find, and you try to construct a plane wave solution, then you find that these odd parity harmonics, they all coupled. And because of that, harmonic number 3, 5, 7, etc. Will contribute to dynamics of harmonic number 1, which is current. And that's what we're interested in if we want to calculate viscosity or conductivity and so forth. So these slowly relaxing modes, which there are many, even though they occur in high angular momenta, they are not benign. They actually make a difference for transport and for current correlator. And you.
Why there is a momentum relaxation if there is no unflow processes here? Usually, if you have collision only between electrons, the only mechanism for momentum relaxation is unflow.
Right. So momentum is never relaxing. It is being exchanged between particles. That's all. So we're discussing the rate at which momentum is being exchanged, and as a result of this exchange.
There is no viscosity at all, so it's just.
So in a way, I'm 2 slides away from showing results for viscosity in this model.
And you have 0 minutes.
Yeah. So but I mean, what I want to say here is that if you do plane wave analysis for linearized Boltzmann equation, you find that in the approximation that odd harmonics don't relax, you get lots of zero modes. You get modes which are 0 on even harmonic site and non-zero sign changing on odd harmonic sites. So they are not relaxing, and they act as some kind of dark states in this problem, and they define a bath that alters the behavior, that couples to first harmonic and alters the behavior of first harmonic. And so in this regime, one can take this approach further and calculate viscosity. And what you find is that there is a range of wave numbers where instead of simple ballistic behavior and before you get into conventional hydrodynamical behavior, you get something in between. Even harmonics are hydrodynamical and odd harmonics are not. And viscosity, if you calculate it by considering shear flow, is scale dependent and has this dispersion. And that translates into scale dependence of conductivity. And if you replace K by inverse width like we did before, you get an estimate for conductance as a function of width for a strip and for constriction and so forth, and so forth. So I think I should maybe, I don't want to show microscopic approach. It's in this paper. Let me just jump to conclusions. So we have this interesting behavior that by introducing collisions and going from ballistic regime to viscous regime, we see increase in conduction, and we can deal with crossover and show that conductance is additive at crossover, and this has been probed in experiment. And then in addition to that, there is this interesting new collective behavior specific for 2D Fermi liquids, which is odd parity hydrodynamics, right? And I mean, one can ask various questions about where this goes. Higher conductance means that dissipation is very low, so how low it can be. Thermal transport, noise, etc. Thank you very much.
Thank you. questions. Let's start. Yeah.
Is there an upper bound on that G viscosity? The conductance is enhanced, as you mentioned, but is there an upper bound also?
I mean, mean free path presumably cannot be smaller than lattice constant, right? But that would make a very weak upper bound. Sorry, cannot be smaller than the Fermi wavelength, right? But so that would make an upper bound, but a fairly weak one. Mm-hmm.
But you almost call it a superfluid. It becomes like a superfluid.
No, it's, I mean, not superfluid. No, or you mean if you combine it with pairing and what? Yeah.
Okay, I'll talk to you afterwards.
Yeah, sure.
Leonid, if I understood you did your. It's very embarrassing. Never mind. It wasn't me. If I understand, you did your beautiful calculate your.
They're still following me. Yeah. Yeah.
You did your Boltzmann solution in this crossover regime, and you found that the conductance was a sum of the two terms.
Mm-hmm.
Do you have a simple argument for why it's a sum of two terms?
No, and I'm not even sure. Okay, so this was done for a particular model, which I didn't have time to explain, but this is a chance for me to do it. So we took collision integral in the simplest form when all relaxing harmonics relax at the same rate. So current is not relaxing, but D, F, etc. harmonics relax all at the same rate. And then for that model, everything else is rigorous, and it follows from the analysis.
Experimentally, it was also C, right? So
I mean,
the model is not an artificial model.
Sure. I mean, experiment. I only know as much as I trust my friends, but theory I know. I guarantee it's right.
Okay, on this positive note, thanks very much.
Yeah.